Um, all right, I guess so. We're going to discuss the dressing factor today. Dressing factor and the asymptotic beta ansatz. So I think previous time I ended at this Magnon S matrix, right? I think that's where we were. Let me remind you of a few key facts. One is the kinematics. So we're talking about magnons that transform in the symmetry SU 2/2 direct sum SU 2/2 of the spin chain, and the generators. So this is kind of centrally extended. So we can think of the ground state as corresponding to the operator trace z to the j, call it L, and the chain, where z is one of the scalars, and the magnons can be identified with some excitations. Let's call them so the magnons correspond to replace one of these with something like phi AP dot, it's like lambda alpha A dot, and D alpha. Well, I guess there's also lambda A beta dot and D alpha beta dot. So where this this AB, capital A, capital B dot, and alpha and beta dot, these are SU2 W indices that correspond to the bosonic SU2 of these super the algebras. This has to do with R symmetry. So this phi's you can think of corresponding to replacing Z with one of these phi's. So these are the in total 6 scalars. So these phi correspond to the other 4 scalars. These are the elementary magnons. Now, of course, you can also try to replace Z with Z bar, but the Z bar is not included here. So these are so if you have one magnon, this corresponds to the states with the sort of the delta minus J. It's 1, where J is the R chart that counts the number of Z's. These lambdas are some fermions, and the D is means the gauge covariant derivative. So you insert this D into in the chain with the Z's. Now, generally, when you apply the supersymmetry transformation, the length of the chain can change, and this is why the phi's are called this the dynamic spin chain. So in the literature, when they refer to this as a dynamic spin chain, it refers to the fact that when the length of the chain might change, and this will have some. So this is something that one has to keep track of. But if you're careful enough, it's not a problem. You can keep track of that. And as we have said before, you think of this magnons as moving with some momentum on the spin chain, and in the limit when the chain is very long, the energy eigenstates are going to be characterized by a set of magnons, finite set of magnons with a definite momentum. We have seen in the magnon dispersion relation, so the momentum P of the magnon and energy, let's call it E of P, let's say, which will be the dispersion relation. Let me remind you that the dispersion relation is 1 plus 16 h squared sine squared P over 2. And we rewrite this in terms of these x plus, x minus variables, which are very important. So these are defined by saying that x plus over x minus is e to the IP, and x plus plus 1 over x plus minus x minus 1 over x minus is equal to I over h, where h is proportional to the square root of the tooth coupling. As we have discussed before, the relation might get renormalized, but it turns out it's not. This Hamiltonian, which is gives the energy, is minus 1 minus 2I h x plus minus x minus. This is a very weird looking formula, and maybe it's more reasonable if I write it as 1 plus 2I h of 1 over x plus minus x minus. So it looks like 1 plus, but both are correct. It's just that in the weak coupling limit, just this x plus x minus is supposed to be large. All right. In any case, so in terms of these variables, one can write the S matrix of so the two-body S matrix, equal to scattering of the magnons will be written in this way, in the following way. So we can write this as so these magnons transform in the fundamental representation with back to the left and the right SU2/2. The constraint on the S matrix basically tensor factorizes. So you can write this S matrix as S left tensor with S right hat. So each of these capture the label of the magnon with back to the undotted and the dotted index. I think previous time I wrote down the form of S hat left, S hat right will be very similar. That is entirely pinned down by the centrally extended SU2/2 symmetry up to overall factor. This overall factor is going to be a phase factor if you assuming unitarity, of course. So that the overall factor is called the dressing factor or the dressing phase. So just to be a bit more concrete, okay, these formulas are rather long. Let me see what let me try to write something more definite. The two special cases where that are going to come up over and over again, the so-called SU2 sector and SL2 sector. Okay, so the SU2 sector refers to the magnon multi-magnon states of the form this phi AB dot. In fact, I refer to this if you just pick a specific A and B dot. So let's consider phi 1 dot. I just pick one of them, and consider another one phi 1 dot. And we're going to assume that so these have the momentum, say P1 and P2. So in fact, as a shorthand notation, which is one I used in notes, which is also standard in the literature on this, I'm just going to put a superscript 1 and 2 on these phis. So this one to just refer to that they carry momentum P1 and P2, nothing more than that. And acting on this asymptotic state, if I act this S matrix on this, I'm supposed to get a transformed asymptotic state. You can think of this as the out basis if you wish, the basis of asymptotic scattering states. So I'm going to get phi 1 dot 2, phi 1 dot 1, whose coefficient is what I call A12 squared, where this A12 was a component of this S left. So remember previously, you might remember that I wrote down the form of the S left hat, which involved 10 different matrix elements. This A12 is the first one. So that's the thing that shows up in this SU2 sector. And for the SL2 sector, we have the same S matrix, the thing you apply it to is D, let's call it D 1 dot 1 and D 2 dot 2. This is going to be equal to D12. Okay, this thing is called D is an accident. So this D had nothing to do with that D. This D is the fourth matrix element in this S hat L that I wrote before, times D2 dot D1. Sorry, I meant the 1 dot, not 2 dot. Like so. Now, I mean, here pictorially you can just think of this as in states and now say that they just cross each other. You kind of, but by the in the usual in the language of if you represent S matrix as actual unitary transformation, this will still be an outstate. So you say that the corresponding in state is the S hat icon outstate, and you re-expand the result on the outstate basis. Let's see. So sometimes we can denote this D11 dot by D plus. That just refers to the fact that this is nothing but the covariant derivative contracted with a null vector. This 1 dot corresponds to a particular four-dimensional null vector. So sometimes we denote this by D plus. Okay, and this D12 and A12 are proportional. So the relation in particular was that, so among these 10 matrix elements of X left, A12 is S12 times X2 plus minus X1 minus over X2 minus X1 plus, and D12 is equal to minus S12. So particularly we have these relations. So in particular, these two are, of course, proportional. They differ by this factor of this thing squared. This S12 is some overall phase, which we have not yet fixed. So now let me discuss what that phase is. So S12 can be written as I forgot if I wrote this from the last time. But again, X2 minus X2 plus minus X1 minus 1 minus 1 over X2 plus X1 minus over 1 minus X2 minus X1 plus. Okay, why am I writing this prefactor? Of course, here I'm just rewriting one unknown matrix scattering phase in terms of another scattering phase. So this is actually what we usually call the dressing phase or the dressing factor. Oh, sorry. What happened? One way one could explain the rationale for defining the dressing factor in this way is just to say that this dressing factor actually is 1 plus order h to the fourth. I think h to the fourth. Sorry, actually, no, sorry. 1 plus h to the sixth. If you express in terms of the actual momentum of the magnet. This is not by no means obvious at this stage. Yes.
Both of these factors are both phases, right?
No.
No.
Hold on. Let's see. Actually, no. Actually, I think maybe they are, because I think the X plus and X minus are in the physical kinematics. I think they are indeed countless conjugates of one another. I think that is true. Yeah, I think they're both phases. But of course, we'll very soon discuss the continuation. So very soon leave the physical domain, but then for the physical kinematics, I think that's correct. All right. Now, at the very beginning, in the first lecture, we discussed the very simple example of the SU2 sector just with a one loop correction. So that can be recovered from the formula. So it's very easy to recover. Let me demonstrate that just so that we be clear about what we're talking about. Let's look at so A12 squared. If you plug this into A12 squared, we find that log of A12 squared is log of okay, there's a little bit of let me see. This may or may not be very illuminating. Okay, let me not actually try to demonstrate. I don't think this is going to be particularly illuminating, but the point is that if you plug this into the A12 squared, you can check that at the leading order in the H goes to zero limit, it actually reproduces this one loop scattering phase of the Heisenberg spin chain XX1/2 XXX1/2 spin chain. So at the one loop order, the result is we express the function of momentum is just independent of the coupling. So one loop means H to 0, and two loop means H squared, and so forth. That's the counting. In fact, at this stage, it's going to be, I think it's going to be illuminating to illustrate a explicit calculation of a scaling dimension just using the formula in the SL2 sector. Let me demonstrate this. Okay, so I'm going to consider the simplest kind of non-trivial state in the SL2 sector. So we're going to be in the SL2 sector with the two magnons on a circle. The momentum is going to be P and minus P, right? And the length of the chain is going to be J. Here, the J is going to refer to the number of Z's. Now, the SL2 magnon, the D is an insertion on top of the Z's. So every time I insert a D, I'm not changing the number of Z's. So it's just adding an extra derivative. Okay. Now, let's write the beta-ansatz equation. This will be the so-called asymptotic beta-ansatz equation because I'm trying to write the beta-ansatz equation, which is just a condition for the periodicity of the wave function. But that's I'm writing on the equation that's A per only valid in the limit when the chain is very long because the input is the S matrix, which is supposed to be asymptotic statement about asymptotic states. This is the asymptotic beta-ansatz. Now you might there's also the so-called algebraic beta-ansatz, but in this context, whenever we say ABA, it always means the asymptotic beta-ansatz. So asymptotic beta-ansatz means that we're trying to diagonalize the wave function of the multi-magnon states under the assumption, pretending that the chain is very long. However, we're going to do an illegal extrapolation of this thing to find a J. This illegal extrapolation is not going to be completely correct because it doesn't account for the wrapping interactions, but we'll come to that later. All right. So if you apply the asymptotic beta-ansatz, I think previous time I discussed the form of the beta-ansatz in the very simple example of the XXX1/2 spin chain. The form of the beta-ansatz will be very similar. In general, you can consider a situation with n magnons, but in the case of two magnons, particularly simple. It just says that the wave function for each one of them is supposed to be periodic. So that is to say that e to the IP times the length is supposed to be 1 up to this phase So that's easy to account for. So the result is 1 is equal to e to the IPJ s. Like I'll write this as SS. So that's basically this. So this I'll just call it S SL2 P1 P1 P. This is the definition. Okay. So SL2 P minus P. Okay. Now let's plug in. So this already, even just with this very simple case, there's already an opportunity for actual result. Let's take the log of both sides. So get 2 pi n. Let's say like minus I times the log of two sides. Okay, I get 2 pi n, where n is integer, right? Is equal to the following. So I get j times I p. J times p, and p. Remember earlier, I guess I just erased. E to the IP is x plus over x minus. So IP is log of x minus. P is I times the log of x minus over x plus. I write this as I times the log x minus over x plus. I have that. And then I have, well, this is just this S12 square. So I just have this thing here. All right. So let me plug that in. Okay, so I'm going to need to use some very small simplification. Okay, there are several things. Okay, there's an extra notation I should now introduce so that it will help us parameterize things. So I had introduce this x variable. Let me now introduce another new u variable. So x plus 1 over x plus. Remember that we have this and this. I wrote the formula. Okay, I shouldn't have erased that. This minus this is I over h. I remember it's I over h. I'm going to define this to be u plus I over 2h, and this will be defined to be u minus I over 2h. Sorry, actually, I put 1 over h in front. 1 over h, u plus I over 2, and 1 over h, u minus I over 2. Okay. So I'm gonna think of this x plus minus as a function of u. You have to be a little careful. This function is multi-value. There's a branch cut. So so when you practice in terms, you have to be careful about which branch you are at. This can often get confusing. But there's convenience for some purposes. So let me use this notation. So here I can write this as okay. So there are these two magnons, which are what I call the 1 and 2. So let me call this P1, and P2 is equal to minus P1. Okay. Let's talk about the U parameter. So what you're going to find is that actually, so you can present this in terms of, instead of the P, you consider U1, and the relation between U2 and U1 is that U2 is equal to minus U1. In particular, x plus minus of U1 is actually equal to minus of x minus plus U2. Let's double check this. So if you swap x plus with minus x minus, you're gonna flip the momentum, so that makes sense. And if you also if you flip the sign of the u here, you are going to swap x plus with minus x minus and x minus to minus x plus, so it kind of agrees with this. Okay. But by the way, I have to say that for all of this stuff, if you want to actually get a feel of it, you have to play with this on Mathematica. You cannot really absorb this just staring at the formula. But in any case, let's proceed. So what you observe here is that so in this very simple, this is like the simplest possible case, right? So in this case, if you plug that into this scattering phase, you see that this is proportional to, so you get minus 2 x1 plus, here you get minus 2 x1 minus. So that thing is proportional to this e to the ip. So it turns out, it's not hard to verify that that you can combine that. So this doesn't get squared. You combine that with this term, and the result of that is you shift this by 1. Shift this by 1. And this factor is going to give you here minus I log of 1 plus 1 over x minus u1 squared of 1 plus 1 over x plus u1 squared plus 2I theta, where I'm gonna always define this thing to be e to the I theta 1, 2 of let's call it x1 plus minus x2 plus minus. I mean, the x plus and x minus are not independent, but it's useful to often to write both because it helps you keep track of the branch structure. So here this will be theta of x plus minus of u1 and minus x plus of u1. Okay, so as I said, u2 is equal to minus u1. So the u1 is really the only variable here. Right? So we want to solve this equation. Now, of course, we cannot actually solve the equation because we don't know what theta is. But let's believe me for a moment that theta, starts is 1 up to for loop and high order corrections. Okay, so let's imagine that theta is 0. Sorry, the sigma is 1 plus high order correction. So let's ignore this for the moment. Okay, let's ignore this for the moment. In fact, before 2006, it was people had assumed that this was equal to 0. Okay. Now, actually, this is an equation that we can actually solve numerically if you have to. So everything is known. You just have to plug into Mathematica and solve it. This is so simple that you can solve this in Mathematica in 15 minutes. And let me describe what the result looks like, which is going to be interesting. I think I can erase this now. Yeah.
Are we taking J to infinity or?
Well, we're going to do something illegal. We're going to take J to be equal to 2.
Okay, but up until now, it's.
Up until now, J should be large. Up until now, J. So the ABA A prime is only supposed to be valid for large J, but we're going to do an illegal extrapolation. We'll understand to what extent it's illegal or illegal soon, very soon. Okay. So I'm going to consider the case J equals to 2. Why do I want to consider J equals to 2? Because J equals to 2 is supposed to be the Konishi operator. Well, this doesn't look like a Konishi operator because I have the D's, but actually it's related to Konishi because it's in the same multiplet. So the Konishi operator, I call it curly K in the notation, is a trace phi I. Now this thing has a descendant, which is well, there are two kind of descendants. There is a descendant that is in the SL2 sector, SU2 sector, which is trace xz times their squared. So if you want to study SU2 sector, you can use that to study the Konishi. In the SL2 sector, it's nothing but trace b plus z minus z b plus square z. So this is the two magnon states in the SL2 sector. All right, so it's SL2 sector with J equals to 2. Okay, of course, it looks highly illegal to try to apply the ABA to J equals 2, but bear with me. We'll see if we can should always try and see what the results are. So with the integrability, you have to be brave to be willing to try such things. And we're often you get pleasant surprises. Okay, so with J equals 2, this is easy enough because let me give you some formula for the expansion in H. Because these are functions with branch cuts. If you want to do this with Mathematica, it's a good idea to always expand this out, perturbing in H. Otherwise, the branch cut is impossible to keep track of. In the physical regime, we're talking about a weak coupling. X plus minus of U1 is going to be, I can expand as U1 plus minus I over 2 H minus H over U1 plus minus I over 2 plus order H cubed. I mean, this is some function with a square root. You can just expand it out. But I write it in this way just to make it clear which branch I'm choosing. So I don't have to think about the square root now. And of course, as you would expect, as I said before, weak coupling H, our convention is always going to be such that the X plus minus are large numbers. We go like 1 over H. And because they go like 1 over H, you can see that because they're large, X plus and X minus are large, the second term is small, right? So leading order in H, you just have this term, and you can very trivially solve for U1. Very trivially solve for U1. So to leading order, U1 is equal to 1 over 2 times square root of 3. Now we're going to keep track of the higher order terms, so you can do this pretty easily with Mathematica. You will find 8h squared minus 20h to the fourth plus 112 h to the sixth plus blah, blah, blah. So you can solve this equation. Now this is under assumption that you set the dressing phase theta to 0. It will turn out the dressing phase will start at current h to the sixth order, and there will be a correction. So the current comes from the first dressing phase. So let me just write it here for now. So I'll just write this as dressing. Okay. Let me tell you the answer at the end though, because I haven't explained how you will get a dressing phase based on the integrability arguments. But this leading contribution from the dressing phase turns out to give a correction which is 48 times zeta 3. Okay, this comes from the dressing, but for now, can you ignore this if you wish. Okay, so you have that. Sorry, I forgot to say that this is for n little n equal to 1. So you can solve this for n into n, but the first non-trivial solution is for n equal to 1. So let's try that because it's kind of the minimal non-zero energy excitation. Okay, so if you use the ABA, once you have solved for the beta, you can usually refer to this U as the beta roots. So once you have solved the beta roots, it's trivial to calculate energy. The energy is just E of U1. For the U2 is the same, where the E is given by the dispersion relation, and you just have twice of that. That's the energy of this two magnon state, and this energy is supposed to be interpreted as delta minus J, where delta is scaling dimension. So this thing is going to give us the anomalous dimension of the Konishi operator in this ABA approximation. Okay, let me tell you what the answer looks like. This is like the usual, 1 plus the dot, so it starts at 1. All right. So let me write down the answer, just to literally plug in the formula I wrote before. There's nothing too fancy. You'll find the expansion 2 plus, just using this formula. Right, 2 plus 12h squared minus 48 h to the fourth plus 336 h to the sixth minus 2020 plus 288 zeta 3 h to the eighth plus dot, where this 3 feeds into that. So if you didn't know about the dressing phase, you wouldn't know about this. But you will know the first few terms.
Is this the first correction?
Yeah, this comes from the first contribution to addressing factor, which only shows up as H to the sixth order.
That's where the dot.
No. The dot dot is a higher order. So this thing is the H to the sixth come from the H to the sixth term in the addressing factor. So that's the kind. But for now you can ignore this if you wish. This is okay. Okay, so what the heck are we doing? We're doing this illegal thing. We're trying to use it to see what can produce the correct anomalous dimension Konishi. So this will be the one loop, there will be two loop, there should be three loop, there should be four loop. It turns out that the one loop, three loop are all correct. That's the actual answer. All right. So it's the exact up to three loop is just correct. Well, it's the magic of integrability. Okay, you know, of course, it's not an accident. In fact, the for loop answer is wrong. Okay, even with addressing factor taken into account, but that is wrong for a very good reason. It's wrong because we ignored the wrapping interaction, and so it's wrong because the ABA is not supposed to apply to the does not account for the wrapping interactions. You see, the wrapping interaction basically have to do with the fact that if you have some L loop planar Feynman diagram that will contribute to this, you can have kind of the Feynman diagram where the kind of interaction wraps around the chain. You need that many loops. You need as many loops as the length of the chain, very roughly speaking, for the wrapping interaction to happen, because you need one particle to kind of go around, but it hasn't crossed all these lines. Every time you cross, you have to add the actual loop because you're talking about planar diagrams. So, so the longer the chain is, the higher loop order you're going to push this wrapping effect, which is why the ABA is supposed to be valid for a sufficiently long chain. For the Konishi, the wrapping interaction shows up at four loop order. This is also a fact that is well, okay. So you see, the thing is, you know, and originally people thought that maybe we'll just get this right on the nose, even to all loop order, but if you have the right addressing factor. I haven't explained where the addressing factor comes from, but okay, we'll discuss that soon. It turns out that the people did the for loop calculation. It was very, you know, this kind of hardcore people, Zenang and others, and the result is does disagree with this. Okay, so this so this is wrong. This is wrong. But it's wrong by a very specific amount that involve some numbers, some big integers plus something times zeta 3 plus something times zeta 5. Those numbers will be reproduced by the so-called mirror TBA, and we're going to discuss that in maybe a couple of lectures from now. Okay, so that's yet another layer of sophistication, which was not known how to resolve in 2006, was understood in 2009. But today we're going to be discussing the 2006 development of the story, which was about the addressing factor. So that doesn't actually help us to determine this of the Konishi, but how about determine some other operator like this one corresponds to the long spinning string. Yes.
So what if I take higher n, like which operator am I computing the anomalous dimension of then? Because J is fixed, right?
Oh yeah. Well, you see, it will just correspond to things that carry higher value of momentum, P. Now, of course, on the case of the length 2 chain, you might say that there is no states with other momentum P. If you have a long chain, then you can have various momentum, right? So at least if J is sufficiently large, you can imagine things, you know, here this is specific momentum combination. But for a long chain, then you do expect to have different two magnitude states with, you know, a set of discrete values. It's expected. Now, of course, you're not going to be able to easily get the details of the Konishi to, you know, to actual precision using this approach, even though here you seem to have some kind of lucky accidents that you're able to get a 3-loop curve.
So somehow the point is that at like fixed J, there is like a degeneracy of states that gets lifted somehow.
But this, of course, we expect. Fixed J, fixed number Mac-down, you still have many solutions, right? I mean, that's the fixed J basically means fixing the length of the spin chain, and also fixing the number of Mac-downs, but you have many states given that. Yeah.
So the point is that if you increase the number of the length of the chain, then DBA is will
It's better.
be correct at higher.
Correct, correct. So the ABA is going to be correct when J is sufficiently large.
So in the case of the long chain, these momentum states, I can think of, as you know, some Fourier transform of the position basis. Should I think of this as literally it's gonna be a sum of just two terms because there's only two positions in the chain here, or should I think of, I'm thinking of like the large J and the continuous P's, and then.
You cannot actually read off the actual value of the P. Let's see. You're not going to be able to read off the actual value of P by staring at this expression, of course.
Okay.
There's no, I mean, of course, here you are, extrapolating the APA to kind of a regime which is a priori illegal. You might hope that you can get the correct energy spectrum, but there's no reason why you should be able to identify this specific value of momentum with just like the position of this. There might be some shifts or whatnot.
Yeah.
In fact, in this case, you can easily see that the momentum is basically, if you write the XP itself, which is this, is like 2 pi over 3. So, here you don't see any it's a 2 pi over 3, but that's what it is. But when you do this kind of try this kind of calculation, if you find that these three numbers match up the three calculation, you have no doubt that you're doing something right. Of course, it's much more spectacular if you can get the for loop, and that indeed is spectacular, but we'll come to that later. Okay, so but now we're gonna return to the dressing factor. All right. The idea, okay, so the dressing factor cannot be determined by the SC2/2 symmetry. The idea is that it's going to be determined by assuming this crossing symmetry. So what does that? So how does that work? So crossing means the following. Okay, so actually before I'm crossing, let me say that we have this S matrix element. Well, they have this S matrix, two-body S matrix S hat. Okay, let's see. Let me write as a shorthand, let me write the S matrix for the pair of particles with momentum P1, P2 as S12. This notation is such that, okay, for simplicity, let's just consider a case where the particle type does not change. So the particle just cross each other, momentum is conserved, so I can just label this S matrix element unambiguously by the momentum P1, P2. I denote this S matrix element by S12. I guess here, maybe I should have changed the notation in my notes because this S1, oh no, actually, sorry. No, sorry. This I actually meant to write the same S1. So I meant to talk about that S12, so that's okay. So we have several constraints. There's unitarity, which were, as already stated, S12, S12 star is equal to 1. So this is the base for the physical momentum. And the next time reversal symmetry, which will say that S12 star is equal to S21. Okay. So together, they imply S12, S21 is equal to 1. Sometimes I think we refer to this as the analytic unitarity relation. This is very useful in studying two-dimensional field theories, two-dimensional S matrix. because now you get rid of the complex conjugations that you can only continue this to complex momentum. Okay, so that's what we're going to consider. Let's consider a general estimation sediment of the form pictorially. Let's say this is 1 and 2 goes into 2 prime 1 prime. Okay, so here I'm going to use the 1 and 2 to collectively denote the particle type as well as the momentum. So so the 1 prime will have the same momentum as 1, but the particle type might change generally. Okay. Now there's a closely related S-matrix element, which is related to this picture by 90-degree rotation. Let me denote this by actually, let me start over here. There's something I call 1 bar to 2 goes into 1 bar prime and 2, where the 1 goes into 1 bar is defined by the following. So when I put a bar on the 1, what it means is to consider the n continuation is defined by the n continuation of the S-matrix element, where x1 plus minus are going to go over to 1 over x plus x1 plus minus. Now, what does that do? So let us recall the following. Okay, so let me remind you. These things are hard to remember. You've seen it once, so repeat these formulas. This I over h, and the energy E is equal to -1 minus 2IH plus minus, which is equal to 1 plus 2IH 1 over x plus. All right. Okay, so you see, if you okay, so first of all, okay, let me see what I was saying. If you send okay, if you send x1 plus to 1 over x1 plus and x1 minus 1 over x1 minus, you preserve this constraint. So that's a legal, at least that's a legal operation. So you're gonna of course send P1 to minus P1 to this, and you're gonna send E1 to minus E1 because of this. Okay, so that's a bit non-trivial now. Right. So this is why it's sort of some kind of weird analog of the relativistic crossing reduction. The relativistic crossing requires flipping the full momentum, say in 4D quantum field theory, and this is flipping both energy and momentum. Despite that, it's not relativistic, but there's a relativistic-like strength relation with the square root, but there's the signs for deformation. Okay, but nonetheless, we can talk about this operation. Okay, so this is some other continuation. So far, I haven't done anything. I'm just saying that you can try that and continue and see what happens. The crossing is the claim. The crossing symmetry is the claim that this or not. That's good. is a statement that, let me just draw this in picture. Okay, so the crossing, the statement that this estimation element is equal to the following. I'm going to rotate this by 9 degrees. So 2 goes in, and here I've got 1 prime C. They go into 1 C. Oh, sorry, this is 2 prime, and here I have 1 C. Where 1 C stands for some suitable charge conjugation matrix acting on 1. Let's just remember the 1 clearly denotes the type and momentum. So, but there's a charge conjugation operation, so far unspecified, that you have to try to determine that its canonicality is associated with this crossing symmetry, such that this crossing will hold, provided you make this identification. The C is something you have to think about what it actually is. So of course, in a situation where you only have one particle, a particle is the same as an antiparticle, then the C is just you can set it to 1. Yeah. So that is the statement of crossing, modulo the fact that you have to figure out what this matrix C is.
And crossing says.
It's assumption. It's a huge assumption, but the assumption is really motivated by thinking about the string world sheets, even though we don't actually know the useful description of string world sheet theory in this context. But based on sort of a semi-classical analysis, or actually even the classical limit, you know, from the world sheet point of view, you know, it's a relativistic theory in a conformal gauge. So you'd expect to have some kind of relativistic kind of crossing relation. But of course, there's a big assumption whether that's continuous to hold. You account for all the quantum corrections. The crossing is completely mysterious from the perturbed gauge theory point of view. In fact, not only is it mysterious, it actually does not make sense in the perturbative gauge theory. It's necessarily non-perturbative without the Tooth count. Because remember, in the perturbative regime, both x plus and x minus go like 1/h. So if you invert that, you're completely taking yourself outside the perturbed regime. So this is something that's totally not visible to any finite ordering perturbation theory. So just the assumption itself is already non-perturbative. Yeah, so this crossing is something crazy that you will never believe that actually exists without some spectacular evidence, but there is spectacular evidence. Okay. So now there is some algebraic way to understand what this matrix C would have to be by consistency with the Young-Baxter equation and the SU2 symmetry, which was worked out by Yannick. I've never tried to understand Yannick's paper, which was very important in figuring out exactly what this C matrix is. But it was just based on some kind of very technical analysis of Hopf algebra that I find it kind of incomprehensible. But without chasing down the details. Nonetheless, it's a shortcut to get to the answer without having to go through all that analysis. So I'm going to take the shortcut. The shortcut is that actually there is a particular matrix element out of the 10 matrix elements that enter this part. I guess it's really 10 times 10 because you have the left and the right, so 100 matrix, which is a lot. But there's a particular matrix element involved in that, where you can understand the crossing, where the C is just identity. It's the following. So let me single out a specific. So let's look at S left. So this acts on. So you have a boson. So I'm keeping track of only the left quantum number now. This is phi and sign notation because you might recall from before. This equals to G12 psi 2 beta phi 1a plus G12 2 psi 1 beta. And here we've got another equation, psi 1 alpha phi 2 beta Could be K1, 2, psi 2 alpha 1. That's L1, 2. Okay, so now of course all these might not have the same dispersion relation, but the type can change, even the statistic can change. If boson can turn to fermions or vice versa, because you have a boson scattering to fermion, it could be boson fermion, or fermion boson. Now we're going to focus on the particularly nice components where they just cross each other. So the boson cross each other, say boson, fermion cross each other, fermion. So in this case, the crossing is particularly simple to describe. In fact, in this case, there's no room for, like the particle type, it doesn't matter. Even if the particle type change, it's still the same matrix element. So this is particularly simple. So with this, because all these G, H, K, L, they are proportional to S12. You know, remember I've written down this long formula. You can look up what they are. So they're all tied to S12. And so the crossing simply, in this case, implies that G to 1 equal to L 1 bar 2. Okay, so now we're in business. Okay, the G and L are related by crossing. Now, if you go back and chase down the relation between G and S12, you will discover that the following. So this implies using this. So it's, you basically can swap one of the S12 with the S1 bar 2. Oh, sorry, S21 with S1 bar 2. You find S12, S1 bar 2. So I'm applying the crossing to one of the factors of this analytic unitarity relation, and I get the following. So because the G and L are not the same as S, but differ by some factor, I had to collect those factors, and the result is x1 plus minus x2 plus over x1 minus x2 plus x2 minus 1 over x1 plus and over x2 minus 1 over. Okay. Now it's probably better to write this in terms of dressing factor, because that's the thing that we want to pin down, and that's, in terms of dressing factor, this says sigma 1, 2, sigma 1 bar 2 is equal to, write this down, because even though this formula is hard to remember, but it's so important that we need to see what it is. Plus x1 minus plus over x2 minus. I feel like this formula are very hard to digest if you haven't spent some time playing with it, because this is 1 and 2 and plus and minus, and sometimes it gets inverted. Like I feel like if you spend enough time studying the subject, your brain gets a little rewired, and you start to be able to absorb these patterns. Okay, so this already tells you, of course, if you believe that we're not being crazy, and if you believe this assumption, then this means that the crossing phase cannot be equal to 1, because it will not satisfy crossing. It has to have this weird, this kind of weird crossing relation. In fact, normally, if you arrive at this, you might think that you have done something wrong, because the right-hand side let me say it this way. The right-hand side is not invariant under 1 goes to 1 bar. Okay, if you, namely 1 goes to 1 bar means x1 plus minus goes to 1 over x1 plus. And just check this, actually just not invariant. So that means sigma 1 bar is not equal to sigma 1. Sigma 1 bar to, okay, so if you do this twice, you don't come back to itself. Now at first sight, you might think that you have done something wrong. But actually there is nothing wrong. The reason for this is that this crossing is very subtle because it has to be defined by any continuation. And if you apply this twice, you are continuing to a different Riemann sheet. And this stressing factor, these are not going to be, single valued functions. And in fact, there are functions on generally kind of infinite sheet Riemann surface that covering the space of let's say the complex U plane. So you have to be cautious. So this does not imply this contradiction. Now, although this sounds kind of crazy, but let's write down the actual formula to so that you can get a better handle on what is going on. It's useful to inspect this in the as always in a limit, either weak coupling or strong coupling. So as I said, this crossing is something that's kind of obscure from the weak coupling point of view. So now let's try to inspect what happens to strong coupling. All right. Let me write down some this now. Let me before let me define sigma 1 2 to be e to the I. I'm sorry, e to the I theta. Let's call it x1 plus minus x2 plus minus. We use this notation. Okay. And so let's inspect this equation. This is the kind of the non-trivial crossing equation. Let's inspect this equation in some detail. So there's a huge amount of physics hidden in this relation. Yeah.
If you plug in the exponentials of x1 and 2 plus minus in with small h, would this thing be 1 until some order in h then, or?
That I think is true. Actually, yeah. Let's see. I think that should be true. Yes. Actually, hold on a second. No. Oh, wait. No. I'm not sure that if that's true because as I said, 1 bar already takes you outside the pressure regime.
Oh,
right. 1 bar is a different kinematic regime, so I'm not sure if that's true. Yeah, we have to be careful. Okay, so let's take this equation, but we're going to look at the strong coupling regime. Look at this regime. So in the strong coupling regime, now we're going to introduce yet another quantity. So earlier, remember I wrote x plus minus. I defined this as 1 over. Sorry, I wrote x plus 1 over x minus. I define this to be 1 over h u plus minus I over 2. Let me now define x to be such that this thing is equal to 1 over h times u. Okay, so this is kind of confusing notation. So I have x plus, x minus, and x are all related to one another. But every time you try to transform, there's the possibility of having a branch cut. So you have to be a bit careful. But at least in the large H expansion, it's unambiguous. So in large H expansion, you can solve easily invert this relation. You can write x plus minus equal to x plus minus H inverse times I x squared over 2 x squared minus 1 plus h minus 2 x cubed over 4 squared minus 1 okay, plus other h minus 2. Okay. Okay, so you can do this. You can do this and you can plug that into that, plug it into the crossing relation. So the crossing relation is going to give us the following. Theta x1 plus minus x2 plus minus plus the cross theta, which is 1 over x1 plus minus x2 plus minus, is equal to the right-hand side. And now you can calculate what the right-hand side is. You'll find that it's equal to 1 at leading order in the strong coupling limit. So the naive crossing will hold in the strong coupling, in the very strong coupling limit. So the naive crossing will hold in the very strong coupling limit. That's sort of the limit where you the asymmetries is governed by the asymmetries of the semi-classical giant magma, which is calculated by Hoffman-Malacina. So in Hoffman-Malacina, you will not see the non-trivial aspect of this this factor. This will just become 1. But then you find H inverse. You just plug this in. This with Mathematica, you find H inverse. Let me write down the formula to show you what it looks like. X2 minus 2 x1 plus x2 plus x1 squared x2 over x1 minus x2 x1 x2 minus 1 x2 squared minus 1 plus other h minus 2. So it looks like this. Of course, it goes on to all others. But as a non-trivial exercise, we can try to find a solution to this equation up to this order. You can see this is non-trivial to solve already. You can try to, usually in the kind of integrated story, whenever you see the relation like this, you try to find the minimal, the simplest possible solution with the nicest and the instruction. Usually that will be the right one. Here's the solution. It looks like this. Let me give you an ansatz for the theta. The motivation for this ansatz is a bit hard to explain. It comes from thinking about the conserved charges on this spin chain. And this was understood by Beiser and Staudecker some time prior to this. And they came up with this ansatz. It says it's equal to chi x1 plus x2 plus chi x1 minus x2 minus chi x1 plus 2 minus chi x1 minus x2 plus. Okay. So this itself actually looks very strange already because before, this x1 plus and x minus are not independent variables. But somehow we want to write it in this way. Okay, this looks a bit bizarre. But anyway, this was something that was motivated by the form of the higher conserved charges on this integral spin chain that they had seen just purely by kind of consideration of these playing with these charges. And they're trying to basically they're trying to see what kind of longer than nearest neighbor interaction of the Heisenberg spin chain that can possibly preserve integrability, and they came up with some structure like this. But anyway, let's take for now take this as an ansatz, and you can take this ansatz and plug into here, and see how you can solve this equation. Of course, we're working this in the strong coupling limit. You will find the following non-trivial solution: chi of x comma y. Right, write this x1, x2. Let me write this x and y. Is equal to h times x minus y. The h is this coupling square root lambda property. 1 over xy plus 1 minus 1 over xy log of 1 minus 1 over xy plus order h to 0. Remember, we're doing the inverse coupling expansion. Okay, so you get something non-trivial, but it's rather nice looking. Okay, so it turns out if you plug this into that, then they satisfy this relation. Anyway, you just have to check it with the Mathematica. It's not, these are the kind of things that, anyway, when you do integrability, you have to play with this kind of things all the time. Very often, it's futile to try to improve things. You just try to find a solution by kind of mathematical experiments. Okay. Now, if you know this, you can get off the ground. By the way, I'm not actually sure what is the original way that the Beiser and friends managed to solve the chi. This approach, so the historical order is a bit unclear from the. It's not easy to reconstruct from the literature because there are these competing groups. But this formula, I first saw this in a very nice paper by Arjuna from Frolov. It's in the string of many papers by the duo. But that was just kind of a small step towards solving for the full solution. So this will get you off the ground. You will know what this looks like at the linear trivial order. But then once you get on the ground, it's possible to try to guess all other ansatz, which is what Beiser, Hernandez, and Lopez did. Let me show you that. So the all other ansatz is chi xy is equal to from 2 to infinity some s greater than r plus s is odd integer, where this goes to infinity as well. 1 over x to the r minus 1, y to the s minus 1, minus 1 over y to the r minus 1, x to the s minus 1. So in other words, it's an odd function under exchange of x and y. With some coefficient, the coefficient you can normalize as 1 over r minus 1, s minus 1, c r s is function of h. So that is an ansatz. This is also an ansatz that Beiser and Stadecker, I think, kind of had guessed based on the kind of studying integrable spin chain. But once you have this ansatz, you can try to guess what the coefficients are. It's a function. It's a 2 integer parameter family of functions of h. All right, and so CRS, according to what we just said, h to start at order h, and then there's some leading terms in 1 over h expansion. So sum CRS n h1 minus n from 0 to infinity. This is a strong coupling expansion. There's also going to be a weak coupling expansion, which I'll come to in a moment. So this is the strong coupling expansion. So what we have seen here, actually, if you just expand this out, you'll find that they're very nicely arranged in this way with CRS0 is delta SR plus 1. So this is something that we already checked from that. So that's for the nice. The remaining, let me erase this now. The remaining coefficients are a bit more complicated. C1 are S minus 2 over pi, R minus 1 times S minus 1 over S plus R minus 2, S minus R. And C R S n for n greater than or equal to 2 is equal to zeta n over minus 2 pi n gamma n minus 1 r minus 1 s minus 1 gamma s plus r minus plus n minus 3 over 2 gamma s minus r plus n minus 1 over 2 over gamma s plus r minus n plus 1 over 2 gamma s minus r. All right, so takes some, especially hardcore people to come actually guess this and check value-based crossing. So that's the solution. All right, that's a strong coupling expansion. That was the result of the paper of Bizert, Hernandez, and Lopez. This expansion has zero radius convergence. It's asymptotic series. That's what you would expect, because this is like alpha prime expansion. The weak coupling expansion is the one I expect to have finite radius convergence, but this is the strong coupling expansion. In fact, because if you only have this, it's actually numerically, unless you can try to do a Borel summation, but it's hard to get high numerical precision. So without doing Borel summation, you cannot even sum it up numerically. Well, okay, you can try to do it for kind of a large coupling, but you cannot. It's not easy to even numerically extrapolate this small coupling regime. Now, it turns out that there is a also closed form of weak coupling expansion, and that was miraculously found just a few months later in the paper of Bizert, Eden, and Staudecker. So the weak coupling expansion, as I said, is actually going to converge, have finite radius convergence. You can, in principle, only continue that to a strong coupling regime and try to match on with this. And that would, in principle, pin down the answer. So let me write the form of the. So the weak coupling expansion is kind of related in a kind of a subtle way. So the weak coupling expansion is it looks quite similar, but kind of a different subtle way. So CR, we're talking about the same function, this function. Let me explain it as some n greater than or equal to r plus s minus 3 c tilde n r s h to the power m plus 1. All right, and the coefficients are c tilde n r s. Let me write this down. 2 cosine pi n over 2. That just means that it's plus minus 1 over 0. Minus 1 to the n plus s, zeta n plus 1, gamma n plus 2, gamma n plus 1, and r minus 1, s minus 1 over gamma n minus r minus s plus 5 over 2, gamma n plus r minus s 3 over 2, gamma n minus r plus s plus 3 over 2, gamma n plus s plus r plus s minus plus 1 over 2. So, if you just play with some kind of numerical experiment and try to naively kind of continue in the parameters and try to do some cross check, you can kind of more or less guess this formula based on that. I mean, it's not going to be a rigorous argument. You have to kind of cross check many things, but it's possible to arrive at this formula without having to reinvent the wheel. Yes.
So how can one have like systematic weak coupling expansion for this? I thought that the crossing, but like is not perturbative or something.
But this is the result. Yes, it is non-perturbative, but I'm talking about the actual phase, the scattering phase. The scattering phase is the Magna S matrix has a weak coupling expansion. Just like you can calculate that using the spin chain Hamiltonian, which has a weak coupling expansion. Of course, the result must have a weak coupling expansion.
I see.
It says that the crossing itself, relation itself relates weak to strong coupling. That has to go through the strong coupling region, but with this end continuation. But the end formula, you have a weak coupling expansion of your stressing factor. It's actual physical observable. And this turned out to even converge as finite radius convergence. As a convergence, has radius convergence, I think, at the some negative value of with this h of coupling itself. So sorry, it has a singularity on the complex h plane. I forgot whether it's at the negative or imaginary value of h. But anyway, all of these things are very easy to deduce once you have the formula. Okay. At this point, let me mention one other important recipe which is that. Okay, let me erase this now. This was the ansatz chi. So the dressing phase was expressed in terms of chi, and chi has this expansion. So anyway, this you can just plot numerically and check that it agrees with that in the strong coupling. It turns out that this thing actually, this analytic expansion, this analytic formula was discovered kind of a couple of years later, actually, in a paper by Doré, Hoffman, and Malacina. So this is known as the Doré DHN formula or representation of this. So all of this might look very complicated, but believe me, by the time you get to mirror TBA and Y system, this will be trivial in comparison to the complexity that will come after. So all right. This is equal to I times the contour integral dz1 over 2 pi I, where z1 so on unit circle integral dz2 over 2 pi I, where z2 has a value circle 1 over z1 minus x z2 minus y times the log of gamma. I think I would be staying within the recording. Let me write log over here. Log of gamma 1 plus IH z1 plus 1 over z1 minus z2 minus 1 over z2 and divided by gamma of 1 minus IH of the same thing, z1 plus 1 over z1 minus z2 minus 1 over. In fact, this DHM representation, okay, this is not so easy to digest, even though it looks kind of potentially nice. But it can clarify some of the underlying analytic structure of this crossing of this dressing factor. And it's quite important to have that formula because this allows the possibility of analyzing the analytic continuation of this into some other kinematic regime in a systematic way. And this will be essential in later talking about this mirror TBA. Yeah, so yeah, I actually have no idea how DHM come up with this formula, but I think they just try to like rewrite this thing in terms of like Bessel functions and play with some integral of the Bessel function and then come up with the formula.
Yeah, I see some equal representation of the Paul-Cramer function that gives you a number.
Well, in any case, I mean, once you have formula, it's very easy to well, it's potentially easy to verify because you know how this expands. So it's easy to check, but I'm just saying that originally when you stare at this, how to recognize that is of this form. I'm not exactly sure how they kind of come up with this representation. But as very often happens in this subject, you just have to play with this formula long enough and understand things better. This is actually a very weird formula. So you can calculate this by simple residue. You can simplify that without expanding the right-hand side. You cannot calculate this by reduce this to simple residue. Some residue contributions. You can try this, but it's when you play with this for a video, you recognize that this is not totally trivial to work with. And it has some kind of unusual analyticity properties, which is not totally easy to deduce. Later in the discussion of mirror TBA, it'll be necessary to continue this into the so-called mirror kinematic regime, and that required the entire paper by Artino from Frollo of 60 pages long to analyze this anti-continuation property. Yes.
So we said that for a small coupling, the x plus or minus are going to be large. So when this formula, like you can have the x and y be outside of the contour or inside of the contour. depending on the age.
Correct. Correct. As I said, this formula is very subtle. This formula, oh, sorry, actually, let me make one comment. I think this, I should have said this. This formula is meant to be only true, actually, sorry, for X and Y outside of the circle, sorry. But yeah, it's meant to be defined by the continuation from the large XY. And another thing that I forgot to say, which is quite crucial, that explains the zeta3 thing earlier. So you can look at, if you look at this recoupling expansion, you'll find that the first non-zero coefficient is C tilde 2, 3, 2, which is turns to be equal to 4 zeta3. This is where that for loop correction, this is zeta3 come from. When I talked about earlier, it says it is addressing factor contribution to the ABA. That's that. Okay. Now, if you only look at the Konishi, you're not going to be able to tell whether it's correct or not because you're missing the rapid interaction. But you can look at some other operator, and this is in the early days. This is what was a known piece of data. So when they came out with this guess, they already knew that they must get this 4 zeta3. So it's there are non-trivial consistent checks to be made. But this also explains the statement earlier that I said. This thing, okay, it's not obvious from this. You have to plug it back in, but the point is dressing phase to start at H26. So start at for loop. Okay. I feel like I probably should stop here because the next thing I will need to explain is to apply all of this to get the customer loss dimension. So that's a situation where we have the operator trace z e plus to the j z. That's the thing that's supposed to describe the long spinning string. But let me at least explain the logic of this. In fact, let's see, do I want to call this J? I think that's probably okay. What are we after? So we want to understand this long spinning string. Now you might say that I'm not allowed to apply this to that operator because that thing has length 2. I only have 2 z's. So how am I allowed to apply the ABA to that? But the idea is that actually for the customer elements dimension, it's such a universal quantity that actually doesn't matter how many z's you put in. So you might as well consider operator like trace z trace d plus k1 z dot trace d plus k l z. If you have l z's, let me erase this formula here. You might as well consider this operator where k1 plus delta dot plus kl is equal to j, right? And I'm going to look at the limit when j is large. The j goes to j is very large. Okay, but actually we want to look at the limit when j is much larger than l, and which is say larger than 1. This is the point where you have to make this assumption of that the asymptotic beta ansatz is applicable in this regime, which is a big assumption. You see, it's not enough because A per I, we're talking about the scattering of asymptotic states. That makes sense if the magnets are sparse. But I'm talking about a situation where the number of magnets is much larger than the number of sites of the chain. So how can you trust this? Well, I don't know why you can trust this. But so this is assumption. This assumption that seems to pass through all the checks, and it's just it's a working assumption that the ABA is valid in this regime. That is to say, the J can be much bigger than L as long as L itself is large. So that's what is believed to be correct. Yes.
But L is small there, right? So
L is small there, but if you only want to extract the customer loss dimension, it doesn't matter. You'll get the same answer.
Why?
Why? Well, because you know, you think about the classical string, right? Because okay, so first of all, in the classical limit, it's clear that you get the same answer. Because we were talking about this string with a very large angular momentum. This Z is some additional rotation charge on S5, but that's not going to matter when it has large angular momentum in ADS5. So it kind of makes sense. But it's supposed to be true. Yeah, it's supposed to be true. I mean, I think one can show this using just the effective action. Think about the effective action. But the point is that the corresponding anomalous dimension, which is the coefficient of the log J in the anomalous dimension of this, is supposed to be as an exact function of lambda or H. It's supposed to be identical for this, regardless of the value of L is. I think I would say that maybe a consistent check is just that you can check in a self-consistent way that if you solve the answer using the ABA, you'll find that the result is independent of L. So that's it's going to be a self-consistency check. You know, this was also backed up by kind of exact this. Oh, but by the way, I should say that the way that this ABA is applicable to finite L is also backed up by the exact analysis at the one loop level using the one loop, because the one loop is a simple, you know, SL2 spin chain is exactly solved, even for finite chain. There's paper by, I think, what is it? Maybe Frolov and some other, Kochemsky and some other folks. I mean, they have analyzed the finite chain with one loop in glory detail, just to solve everything exactly. And it's consistent with the idea that ABA would be applicable in this regime. Of course, that doesn't prove that when you include all the dressing factor and stuff, it still apply, but that is the working assumption, which we believe is correct. But this is, you know, this is just one of the number of assumptions that I said before. That's I don't believe has been justified from first principle. Okay, so anyway, to actually get this from the dressing phase is then a standard exercise of taking the ABA and take the limit of large number of magnons, and you do some kind of approximation with some density function. I think it's better to leave that the next time because I think we're already, you know, it's already been a lot. So that'll be it for now.